Hey guys, this is our last set of notes for this unit about uniform electric fields, which we sort of already touched a little bit on. Uniform electric field, the word uniform means being the same throughout. And a uniform field is basically considered two lines of charge. And the field itself, remember, we always test a field with a positive small charge. Let's get a little light in here for a second. So which way would a positive test charge go? Well, in an electric field like this, it would go positive to negative. So we need to just draw that in. It does curve a little bit. A lot of times they're called lines of charge or plates of charge because it's usually a piece of metal, like aluminum or different metals. The electric field inside has got a uniform strength based on the voltage divided by the distance. Now I'd like to cross multiply this and we get a formula that we call V equals ed. That way it's just a little easier to remember. D would be the distance between the two plates of charge or lines of charge. E is still electric field strength. Remember, we're gonna have a new unit here because if I were to look at this, this is gonna be volts per meter. So we have two units now for electric field strength. I don't care which one you use, they're equivalent. And then potential difference, which is measured in volts. It's a pretty simple formula. This is definitely something that we use for something called a capacitor. What is the electric field strength? So that's going to be E between two parallel plates. As soon as you see that, that's how I know I use this formula. It's a uniform. Here's my voltage and here's my distance. Of course, that's going to have to be converted. All right, so E equals 2,000 divided by 0.001. Okay, you can divide that out. I don't need to bring a calculator. You're going to get 2 times 10 to the 6, or 2 million. And I'm going to use volts per meter, and I don't care if you use volts per meter or newtons per coulomb. So volts per meter is another unit. Okay. What voltage must be applied? So that's a V. Two parallel plates, that's how I know this is a uniform problem. 1 centimeter, that's a distance, to have a field of this strength, so that's an E. So that's how I identify these, okay? So I'm gonna use the different form of this, V equals ed, just to use that. So V equals 7 times 10 to the 5th times 0.01, okay? Because we gotta always be in meters. And if you times that out, you're simply gonna get 7,000 volts. I didn't bring my calculator out for that. There's an electronic device called a capacitor, and they're used in all sorts of devices. Tasers are a really good example. They store up electric fields inside the plates and then they release it quickly to tase somebody. Cameras also use them for flash, for the lights, for the flash. So there is an experiment, and I'm going to show you a little bit about this experiment in just a second. I'm going to bring up my iPad here so you can get a visual. I'm going to turn these out of the way so you don't have to see the reflection. So Robert Millikan, American scientist, used oil drops in an apparatus that had charge plates. I'm going to show you with this little simulation. I'm going to zoom in a little. This is a very simplified version of this. You can see up here there's positive charge, down here there's negative charge. And he had this little spritzer that he would spray, and he would adjust the voltage in there, and the charges, because this was a little atomizer, the drops would have charges on them, and he could suspend them. So if I spray this, you'll see this little simulation will get one of the charges to stay still. I didn't need to stay still. Let's try it again. Usually we get one. But in the real experiment, he had to control the voltage and get it to stay still. So basically, one drop is balanced because it has weight that's pushing down and it has charge that's trying to push itself up. It's a negative charge, okay? So it's trying to push up because here's negative, here's positive, but its weight is balancing it. Okay, we're gonna look at that just in a minute more, but that's basically what the setup looked like. So in this situation here, EQ is the electrostatic force because that would be the up force would balance the down force of gravity. And when he would get those balanced, he could use this information to figure out how much charge. And he did this over and over and over. And part of what he found was all of these charges occurred in a basic multiple of 1.6 times 10 to the negative 19th. It's kind of like the lowest common multiple, like in math back in the day. And that's how he came up with this 1.6 times 10 to the negative 7th. All right, so let's use the first, this is a simplified version. Then we're going to use that sample and show you how you do how a little bit more intricate math. So let's say we have a field of 1.92 times 10 to the 5th newtons per coulomb. That comes from the two parallel plates, and an oil drop with this mass. Well, the mass of that is not so easy to find, and we're going to show you with a harder example. The goal here was to find how many charges. In other words, that's our whole number. So we're going to use this EQ equals mg. So E, 1.92 times 10 to the 5th times Q, which is what we're looking for, equals M, which is 1.57 times 10 to the negative 14th times G, which is gravity, so 9.8. All right, so let's see what we can get for this. I'm going to have to do this one out. All right, so 1.57 second negative 14. Oops, not clear. Let's try that again. 1.5 second EE negative 14 times 9.8. So that's this side divided by 1.92 second EE 5. All right, so we get this. So Q equals 8.01 times 10 to the negative 19th coulombs. That's not the question asks. The question is, how many excess charges is it? So now I have to divide by the 1.6 times 10 to the negative 19. All right, so divided by 1.6 second EE negative 19, and we get 5.000. Remember, when you're talking about charges, you have to round to the whole number. So in this case, the answer is 5 excess charges, or 5 electrons. That's how much. And he did this over and over, and he kept finding all of these numbers to show up, and he found that the lowest common multiple was this. All right, so we're going to turn over on the back, and we're going to use this space for an extra example. So I'm going to go back to the iPad.